In this video, we'll look at more examples of vectors in three dimensions. In this first example, we've been told that, well, this is not an example. We are simply just learning about I, j, and k here. You might see these units again and again, and these are the vectors that go in, or rather the unit vectors that travel in x, y, and z dimensions. So every time you see a letter I in front of a number, you should automatically associate that this letter or the coefficient of I is traveling in x direction. The coefficient of j travels in y direction, and the coefficient of k travels in z dimension. Okay, so now looking at the first example here, we've been given these 2 points, and we've been asked to find the position vector of A in column notation, where I, j, and k are in column notation. So, just like previously, to find the position vector, all we have to do is rearrange them in column notation. We'll have 1, 5, and -2 in front of, or rather in as coefficients of I, j, and k. And position vectors are actually where you can just write them on a single line, on a straight line, without any brackets, as long as you put I, j, and k in the right places. For B, we had 0i, therefore we don't need to write it. So in part B, we are asked to find vector A to B as a column vector. So this is where you subtract position vector A from position vector B, because as we said earlier in earlier videos, we have to travel downwards from A to origin and back to point B. Okay, so that's what we are going to do. We're going to take away position vector A from position vector B. Now, it's easier to write them in column notations to see which numbers match up with each other perfectly well. 0 minus 1, 3 minus 5, and 7 minus a minus 2 will give us those values. So in the next example, we've been given vectors A to B in column notation, and we've been asked to calculate 4a plus b and 2a plus 3b. That means 4 lots of vector A added to vector B. All we have to do is multiply the coefficients with each other and add them together. So let's answer part A first. 4a plus b. You multiply 4 by each and every value in the vector, and then you add the second vector b. So 8 plus 4 is 12, minus 12 plus minus 2 is minus 14, and 20 remains as it is. And then let's look at 2a minus 3b. We're going to multiply both vectors with 2 and the other vector by negative 3. Therefore, we'll have 4 minus 6 and 10, take away 12 minus 6 and 0. We end up with minus 8, 0, and 10. Let's put it in the bottom corner there. Now let's read part B here. Part B is asking us to state with a good reason whether either of these vectors are parallel to a third vector 4i minus 5k. Now here we have to do some exploration here. We can rewrite this 4i, this vector as a column vector. 4 travels in x direction. We have 0j, so we put a 0, and we have a negative 5 here. Now, we've been asked to find the parallel vector. Parallel vectors, if you remember from year 12, are multiples or fractions of each other. They don't have to be exactly the same length. They can have different lengths. As long if they are parallel, the coefficients will have the same ratio. I'm going to give you an example. For example, if I have 2, 3, and 5, and on the with a parallel vector, it doesn't necessarily have to even point in the same direction. It can point in the opposite direction. I may have -4, -6, and -10. This vector is a multiple of the other vector, because when I factorize a -2 out of it, I will have 2, 3, and 5, which is the first vector here. Therefore, these two vectors are parallel with each other. The right, the shortest distance between them can be found by a perpendicular line. In any case, so let's get back to this example here. We see that 4 and 12 are multiples of each other. So we'll see, we will say that perhaps this vector 4a plus b might be three times as big as this vector. So let's multiply it by 3. If we multiply this vector by 3, we'll have 3 times 4, 3 times 0, and 3 times -5, which will give us 12, 0, and -15. Is this the same as vector 4a plus b? No, sadly, this is not the same as 12 minus 2 minus 14 and 20. Now you could take any other factor and say check whether if you multiply -5, for example, by some number to get 20. If you do that, again, you're not going to get this vector exactly, because the 4 times -4 will be -16 and won't match up with 12. So we say no, this vector is not parallel to 4i minus 5k. I'm gonna do the rest of my work in a different color so you won't get confused. This vector is 2a minus 3a has -8, 0, and 10 as its components. So we look back at the original vector that we have here. 4 times -2 will give us -8. So let's see if 4, 0, and -5 multiplied by -2 will give us that vector. Yes, I'll get the -8 first, and then 0, and a +10. Is this vector the same as the vector we have down here? Yes, they are. So therefore, they are parallel vectors to each other. This is parallel, and the other one is not. Alright, so let's look at another example. Before we go any further, let's uh, look back at what we found to be unit vector in year 12. To calculate the unit vector, we had to find the magnitude of the entire vector and divide each component of the vector by the magnitude, so that the final result would give us the length of the vector to be 1. Okay, so let's say we have two components to the vector. Let's say they're A travels in I, and B travels in J. We have simply vector A, AB, which is in 2 dimensions. The length of the vector, let's call it vector AB, its magnitude is given by the square root of a square plus b square. So we're dividing by the magnitude to find unit components of the unit vector. The unit vector also works in the same fashion in 3 dimensions. So all we have to do, we have to find the length of the vector and divide by the magnitude of the vector. Find the magnitude of, this example asks us to find the magnitude of A, which is equals to 2i minus j plus 4k. So first we need to calculate the magnitude of A. We take Pythagorean theorem and we put the formula in action. The magnitude is the square root of 21. Therefore, the final answer, 2 has to be divided by square root of 21, minus 1 will go over square root of 21, and 4 goes over square root of 21. Okay, so this is one way of writing it. Another way is to write it as column notation and have 2 over root 21 minus 1 over root 21 and so on. In this next example, we've been given that vector A is 2I minus j and fold k. The magnitude, actually, this is the same example. The magnitude is 21, the square root of 21. Now we are asked to calculate the angle between the, the vector and x, y, and z axis. So, if we do some digging, we'll figure out that the angle can be calculated with right angle triangle here. If we drop the point A and drop a shadow, draw is projected downwards on the x-axis, we'll get a right angle between the tip of the arrow, the tip of the vector, and the x-axis. This is the shortest distance. What we are concerned with is this uh, this length and the hypotenuse of this triangle, which we already know is the square root of 21. All we have to do is apply some basic trigonometry, that's some rudimentary trigonometry, and that's telling us adjacent divided by hypotenuse is a cos. So therefore, we'll take the cos of these two values. We know that in x direction we have already only traveled 2 units. So we divide 2 by square root of 21 and take cos inverse of that. Okay, so cos inverse of 2 over root 21 gives us 64 degrees, 64.1 to be exact. We do the same thing for x, y, and z. We do the same thing for y and z as well. So if I rub off what I have here, next we have a minus 1 in front of j. So we're going to take theta in z in in y direction to be minus 1 over root 21 and take cos inverse of that. Then we do the same thing for z direction. We take the 4 that is in front of k, divide by square root of 21 and take cos inverse. In this example, we've been asked to calculate that we've been told that points A and B have position vectors such and such relative to the origin. Origin is O. So we are asked to calculate vector A to B and show that OAB is an isosceles triangle. So if we make a quick sketch here, we're not sure exactly which of these vectors are the same length of each other, but one of these three vectors have to have a pair of these two have to have the same length. So let's calculate A to B. That means that we subtract A from B. So let's do that. 3 minus 4 is a negative 1. 4 minus 2 is a 2. And minus 1 minus 7 is minus 8. Now we have three vectors. Is there any way that we can guess which one is equal to which? Not really. So let's apply the Pythagorean theorem to each of them separately. First, we'll find length AB, and that turns out to be square root of 69. Next, we calculate OA. Length of or magnitude of A is square root of 69. Bam, these two are the same. Perfect. But let's just, for example's sake, calculate the length of OB as well. OB is different. So we do indeed have a right angle triangle. Not we have an isosceles triangle. Okay. Okay, so let's look and see we have no, we don't have any other example.